Thank you. All right. Hello, everybody. Welcome to the second of our three Gemini grad visitor talks. So we'll have one tomorrow as well. But today it's my pleasure to introduce Changseok Kim from Seoul National University, where he is a PhD candidate. And so apparently we may be getting a preview of his PhD defense in a couple of years. So he is a double major in astronomy and physics education. So if we have any questions about physics education, we're gonna definitely ask you about it. And then research interest should appeal to a large number of people here because he's interested in AGN feedback, gas outflow, and galaxy evolution. So that I think is like half the staff here. So yeah, take it away.
So, yeah, thanks for the nice introduction. And my name is Changseok Kim from Seoul National University, and my supervisor is Professor Chong. And first of all, thank you for giving this nice opportunity to visit here and give a talk about my recent research works. And in this talk, I will talk about my previous research results and also my ongoing project. So especially based on Gemini data. So I think, as I said, Jack, maybe it's maybe 2 years early preview of my thesis defense talk, but we'll see. I hope everything goes well, but yeah. So let me start. So the title is Temporal and Spatial Constraint on AGN Feedback via Gas Outflow. Yeah. The screen is okay. So yeah, so we now all know that the supermassive black hole reside in the center of the all-massive galaxy. So some of the supermassive black hole shows a very luminous shown as a very luminous object at the center of the galaxy, so which is called the active galactic nuclei, AGN. So we thought that we are thinking that this is occurring in supermassive black holes. So supermassive black hole itself is very interesting object to study, but it is also become very important in terms of galaxy evolution since the discovery of the correlation between the supermassive black hole masses and the host galaxy properties such as M sigma relation shown in the right figure. So we now believe that the supermassive black hole and galaxy co-evolve and regulate each other's growth, so-called co-evolution. I think I need to click. So yeah, as a mechanism of the co-evolution, agent feedback mainly suggested. So this agent feedback means that agent activities such as radiation, outflow, or jet affect the interstellar medium and regulate the star formation in its host galaxy. So in the left figure shows a cartoon of the agent feedback readings such as etc. So AGN is shown as the black hole growth and the star formation shown as the galaxy growth. So they share the same gas reservoir as a fuel and give a feeding and feedback and give an impact on each other. So this is the scheme of the agent feedback. And it is also the essential ingredient in galaxy evolution model to reproduce the star formation quenching in the massive galaxies. So among the various phenomena from the AGN, agent-driven outflow is often suggested as an efficient channel of feedback. So this agent-driven outflow can suppress star formation by directly removing or heating or disturbing the interstellar medium. So there are several reasons why this is the efficient channel of the agent feedback. The first, this agent-driven outflow is very prevalent in AGNs, and especially in luminous ones. So this left figure shows the x-axis is the agent luminosity or Eddington ratio, and y-axis is the outflow fraction. So how many AGNs shows the outflow? As you can see, the luminous one tends to have more outflow and very luminous regime. You can see that almost all of the agents have the outflows. And second reason is that several observational studies reported that the galactic scale outflows exist, and so it can affect the galactic scale interstellar medium. And also lastly, it is necessary to in simulation to reproduce the star formation quenching. So these are the why the outflow agent-driven outflow is efficient channel of the feedback. So to understand the physical properties and to study this agent-driven outflow by observation, O3 5000 Ångström emission line is often utilized to trace the kiloparsec scale AGN-driven outflows. So the right figure shows the O3 narrowband imaging of the nearby active galaxy. So the green shows the O3 image, and you can see the biconical structure of below and above the galactic dust plane. So we often suggest that this a biconical outflow model. And if you observe this biconical outflow by spectroscopy, then we can only detect the blue shifted cone which is approaching us, and the receding cone is getting weak due to the dust obscuration by the galactic dust plane. So in the spectroscopy, in the left figure, you can see the blue shifted wing component, the wing outflow component, and the narrow core component, which traces the gravitational potential rotational movement of the galaxy rotation. So yeah. So in our previous study, we directly compare the star formation rate and versus the AGN activity. So these two figures shows the main result of the previous studies. So the y-axis is the same as the specific star formation rate, which is the star formation rate normalized by stellar mass. And x-axis is in the left figure, x-axis is the outflow strength. And in the right figure, x-axis is the Eddington ratio. So you can see that they have the positive correlation between them. So if AGN suppresses the star formation instantaneously, then this trend should be opposite, which means that luminous AGN should have the smaller star formation rates. So this positive correlation suggests that there is no sign of instantaneous star formation suppression by AGN.
This question.
Yep.
How are star formation rates measured in these cases? It's notoriously difficult with AGN activity.
I will explain the details, but in this, because this is a large sample of SDSS AGN, we mainly use the artificial neural network based star formation rate from the Ellison et al. 2016. But I will show some of the star formation rate results in the later part of this talk. So despite the many observational studies on AGN feedback, we still don't understand fully understand how the AGN feedback works, and especially when and where AGN feedback works. So through my PhD studies, I'm studying to give a temporal and spatial constraint on AGN feedback. So in this talk, I will introduce the temporal constraint on AGN feedback. So determining star formation rates of AGN host galaxy. And second, I will show the spatial constraint on AGN feedback. So mainly focusing on measuring outflow sizes. And lastly, I will introduce my ongoing project on post-starburst AGNs. Yeah, so it's the part one, the temporal constraint on AGN feedback. So this part is based on the Kimura 2022 paper. And as Brian asked me, so there are many star formation rate indicators. So let's recall the star formation rate indicators in normal galaxies. So in this bottom panel, you can see the left to right, you can see these small star formation rate galaxies, quenched galaxy to the star forming galaxy. And you can see that where star formation rate gets higher, then the more spectrum gets more bluer and more stronger emission lines showed. So we mainly use the star formation indicators, which traces mostly the young and massive stars. So maybe spectral modeling, color, UV emission, emission lines such as H-alpha or O2, radio, or far infrared continuum. However, the main problem to AGN host galaxy is that AGN is a very bright source, and its radiation almost spans from gamma ray to the radio. So many of these star formation ray indicators are contaminated by AGNs. So for example, spectral modeling, color, UV emission, all contaminated by accretion disk. And also emission lines such as H-alpha also contaminated by the narrow emission lines of the AGN, and also radio emission also contaminated by the jet. So one of the solutions is that far infrared continuum emission by the dust. So in the bottom figure shows one of the AGN spectral energy distribution of one of the AGN host galaxy, and the red line shows the dust emission by the star formation, and green line shows the dust emission by AGN dusty torus. And you can see that the far infrared regime, maybe near the 100 micron, there is almost no agent contamination. So we can use far infrared continuum as a star formation indicator for agent host galaxy. Yep.
What do you assume as temperature of the dust? Do you have a general value or you have more points of it?
You mean the temperature of the dust?
Yes. Then now you are assuming that how many measurements on the far infrared you have to estimate the shape of the SED?
Actually, yeah. In this SED modeling, I will introduce some of the examples, but I think mostly they have 2 or 1-ish far infrared detection or sub-millimeter detection, because the sensitivity issue and many other data availability issue. But in this case, in our case, we only focusing on the dust luminosity, not the dust physical properties of the dust. So yeah, we are using this data. So is it?
Just the question that to get the final far infrared emission, you have to do the integral of the entire modified black body. And so depending on where you sample the SED, you have better handle what is the global shape of it.
I think in our cases, we cannot constrain the detailed shape of the dust particle, dust emission, because as I say, it's a lack of dust data flux points at the point. Yeah. So the best tracer for the far infrared emission is near the 100 micron, but this is limited in the ground-based observations. So we use the JCMT Scuba 2 sub-millimeter data to trace the Rayleigh Jeans tail at the sub-millimeter regime. So this JCMT Scuba 2 can observe the 450 and 850 simultaneously. So it is the optimal for our studies. So the goal of this part is that the test previous I showed the positive correlation between AGN and star formation. So the goal of this study is to test the AGN activity and star formation correlation based on far infrared based star formation with sub-millimeter data. So the sample sample consists of 52 STSS AGN with 39 type 2 and 13 type 1 AGN at redshift less than 0.2. And we use the SIGA code, which is the Galaxy SED modeling code from the recently improved as X-ray, but in this time we used from the UV to radio. So the SIGA code estimates the physical properties based on the Bayesian scheme, and we measure the infrared luminosity by SIGA and use this conversion equation from Pennicutt 1998 and obtain the star formation rate based on far infrared luminosity. So these are the example of our fittings. So left one is when there is a far infrared near 100 micron and sub-millimeter both exist, and right one shows the only sub-millimeter data exists. So yeah, this is it is the main result of this study. So we test the previous positive correlation between AGN and star formation with this far infrared based star formation rate. So as you can see, these big colored points are our scuba 2 sample, and small dots are the parent sample from the SDSS AGNs. So as you can see, this y-axis is the specific star formation rate, and x-axis is the outflow strength and Eddington ratio respectively. And you can see the positive correlation between them. So we also we confirm that there is no instantaneous AGN feedback by the outflow. So this gives some kind of temporal constraint on AGN feedback. Yeah, we interpret this relation with the delayed feedback scenario. So when there is a common gas supply, such as merger, then it enhances the star formation and AGN simultaneously. And AGN is a certain time scale to quench star formation. So both are getting down in this direction. So this is called, we call it as a delayed feedback scenario, and I will talk about it in the part 3. Sorry. Yeah, so the part 2 is about the spatial constraint on AGN feedback. So this is in this part I use the Gemini GMOS IFU data and also the 3D outflow modeling code. So this is all Gemini part. The GMOS part is based on the Kimura 2023 paper. So
May I ask a question on the previous part? Sorry to interrupt your second part.
Okay.
So are you able to place any constraints on the delay time between when the AGN is triggered and then the quenching occurs, and also any timescale on the quenching based on these results?
We cannot constrain this by this result, but I will explain in the part 3 how my plan how to constrain these time scale explicitly. So
okay, I'll wait.
Yeah, sorry. Yeah, so integral field unit in IFU is as all of you know, that powerful instrument for the IFU studies. So shown in the top left panel is it can obtain spectrum from each pixel, so we can analyze the outflow and gas kinematics at each position of the galaxy. So with this IFU data, we can obtain the kinematic structure of the outflow. And also, based on BPT diagnostic, we can also analyze the photoionization state of the AGN host with a spatially resolved view. And also, we can measure how large outflows are, so the outflow sizes. So we have performed the GMOS IFU survey of the AGN-driven outflows. So basically, to investigate the spatially resolved outflow properties in local AGNs. So previous studies only focused on the type 2 AGNs with strong or weak outflow. And in these studies, we included the type 1 AGNs to the samples to get a more comprehensive view. So the goal of this study is to get a spatially resolved properties of the gas outflow and constraint on its size. Yeah, there are a total 45 AGNs, including archival targets. So 16 are new targets from this study. So type 1, among the 16, 11 are type 1, so observed in 2019, and 5 are type 2 observed in 2016b. So they are all selected based on the luminosity and outflow strength, which is outflow velocity dispersion normalized by stellar mass or the stellar velocity dispersion. So these are the 16 new targets in this study. So these 11 targets are the type 1 AGNs, and these 5 targets are additional type 2 AGN. And in the right figure shows the velocity dispersion diagram of our GMOS sample and the parent sample shown as small dots. So this VVD velocity dispersion diagram is basically show the outflow or gas kinematics of the AGN or any other emission line galaxies. So mostly small dots, the parent sample located near the velocity equals 0 or small velocity dispersion regime. But our sample, as you can see, they are mostly located on the very extreme regime. So this indicates that these targets has a very strong outflow. So in the spectral modeling for type 1 AGNs, basically we model the emission lines, including both broad line and narrow line region, by the multiple Gaussian. And also accretion disk was modeled by the power law continuum, and iron 2 was modeled by the Gaussian convolved template from the Borson and Green 1992. And in type 2, narrow lines also modeled by multiple Gaussian, but stellar emission, stellar continuum was modeled by PPXF with E-Miles templates. Yeah, so these are the velocity maps of the O3 in the left and H alpha in the right. And as you can see, the O3 velocity maps, all 16 targets shows the blue shifted region at the center. So this means that this consistent with the approaching outflow cone of the biconical outflow model. While the H alpha, of course, some of them shows the blue shifted region at the center, but mostly they have the blue and red shifted pattern. So this indicates the galaxy rotational rotation. Yeah. And secondly, we also analyzed the photoionization state based on BPT diagnostics. So these are the BPT maps of our total 31 GMOSI sample. And each color means the different ionization source. So AGN for red and liner orange, and composite star formation as green and blue. So obviously our targets are selected by the luminous AGN. So AGN photoionization is dominant at the center. But many of them shows that the structure, the liner and composite star formation surrounds the central AGN region. So this is mainly because the AGN is dominant at the center, but it becomes weaker at the outer region. So other ionization sources become dominant in the outer region. So this kind of ring structure shown. And we also mark the H alpha detected region, which is the region where the H alpha is detected, but one or more of the other BPT lines are not detected. So with the light blue color. And we also draw the outflow size as a black circle shown here. And you can see that these H alpha detected regions you can consider this region as a potential star forming region. And they are you can see they're more extended than the outflow size. So this potential star forming region tends to be more extended than the outflow region. So outflow can affect the central region, but not the disk or galactic scale star formation. So now I'm gonna explain how we measure the outflow size based on kinematics. So based on the O3 wing and core, the outflow and rotation components, these flux velocity and velocity dispersion maps, we calculate the second moment of the O3 emission line with this formula. And we normalized it with the stellar velocity dispersion and plot it as a function of the distance, angular distance from the galactic center. So this is the result of the right figure shows the normalized velocity dispersion as a function of the angular distance. And you can see the decreasing trend. So if there is no outflow, then the O3 velocity dispersion should be similar level to the stellar velocity dispersion. So that ratio should become the unity. So we define the outflow size where the sigma 3 over sigma star becomes the unity, and obtain the outflow size of the 15 among the 16 new targets. So then with these outflow sizes, we plotted this outflow size as a function of the O3 luminosity, and shown in the right figure. And you can see that the positive correlation between the outflow size and the luminosity. So this means that the more luminous AGN has larger outflow sizes. And also the blue points are type 1 AGN, and this type 1 AGN also shows the similar positive trend with the type 2 AGN. So maybe in terms of unification model, maybe the viewing angle is not a critical factor to determine the outflow size. And we performed the linear regression of this sample, and we obtained the slope of 0.29, which is almost similar to the Kangenu 20 18 paper, which only used the type 2 AGNs. However, if you focus on the outflow size, the value itself, then it is most of them are less than several kiloparsec scale, or maybe mostly a few kiloparsec scale, except for several targets. So for example, if you assume an AGN with the Eddington luminosity of 10 to the 8 solar mass black hole, then our relation gives a 3.5 kiloparsec scale outflow. So this means that the outflow size mostly confined up to several kiloparsec scale. So it cannot affect the global scale or galactic scale interstellar medium or star formation. So this gives some spatial constraint on the AGN feedback. So these are my previous results, and I'm gonna show you some preliminary results of my ongoing project. Firstly, the 3D biconical model. So in our previous study, BNU 2016, we already did some analysis on using the toy model of the 3D biconical outflow. 3D biconical outflow. So this model includes the 3D biconical structure with the kinematics and geometry and flux distribution, and also with the dust extinction very simply implemented. And with this 3D biconical outflow model, we collapse through the line of sight axis, and we get these flux velocity and velocity dispersion maps. So these were our previous study. So there are we improved this previous toy model with three major points. So first thing is we added the seeing effect to our model. So in these figures, you can see that this one top panel shows the seeing is not included, and the bottom panel shows the seeing is included. So you can see some more blurred image in the bottom. And also second, we added the rotating disk component in our model using the Galpax 3D and package. And third, we simply corrected some modified the code to reproduce to make the mock data such as GMOSI pure SDSS more realistic. So with these three improvements, yeah, we firstly make the outflow model and the disk model with the given parameter set, and we combine them like this and adopt the seeing convolution here. We finally get the 2D maps of the flux velocity and velocity dispersions. So if you use these three maps directly, then we can consider this as a mock IFU data. And if we extract the velocity and velocity dispersion at the central 3 arcsecond aperture, then we can use as some kind of mock SDSS data. So I will show you how we use this mock IFU and mock SDSS data in our study. The first thing is mock IFU data. So with the mock IFU data, one thing we can do is that we can test the method for measuring the outflow sizes because we know the answer of the outflow size. So we can just apply the previous literature methods to the model and test how well this method can measure the outflow size. So in this simple test, there are two models in this example. So they have the exactly same physical parameters, but one thing different is the redshift. So redshift, left one shows when redshift is 0.05, and right model shows when the redshift is 0.2. And both models have the outflow size as 1 kiloparsecs. So there are many outflow size measurements. So among them, we only use two kinds of outflow size measurement method. First thing is, as I introduced in the previous part, this first thing is the velocity width based method. So in this method, outflow region is defined where the velocity width is above certain level, certain criterion. So in our case, sigma of 3 is larger. Outflow region is where the sigma of 3 is larger than sigma star, and WAD, which means that the velocity width that includes the 80% of the total flux of the O3 emission line. So in the WAD method, they used the criterion as a 600 km per second. So they use this velocity width as a outflow size measurements. And the other one is the spectral astrometry based method. So in this case, we only use the Carniani 2015 method. So in this method, they firstly draw all the channel maps in each velocity bin, and they measure the flux centroids of each channel map, and they define the outflow size where this maximum offset of the flux centroids. So among these flux centroids, they define the outflow size where the maximum offset. So this is I think, kind of bad news to our study, but I will show the preliminary result of this outflow size measurement test. So right figure shows a similar plot, but it's the y-axis is the width, velocity width, maybe WAD or sigma 3, and x-axis is the distance from the galactic center. And the blue one shows the WAD velocity width, and the yellow one shows the sigma 3 velocity width. And in this case, redshift is 0.2 model. So the real outflow size, the given in the model, is located here, while WAD and sigma 3 located even here, very overestimated. And spectrometry is very underestimated compared to the outflow model. And the red dashed line shows the seeing size, half maximum of the seeing size. So in this case, the outflow size is comparable to the seeing size. So this seeing effect caused the overestimation of the velocity width based method. So this is kind of bad news for our study, but I will, this is a preliminary result, so I will go through how to measure the outflow size well in the future. And next, I will talk about the MOOC SDSS data and how to use it. So in Wu et al. 2016 paper, we already showed the velocity dispersion distribution of the 39,000 SDSS type 2 AGN at redshift less than 0.3. So these are the VBD diagram of the almost 40K SDSS type 2 AGNs. And BNO in 2016, we already tested how well the outflow model reproduces the velocity dispersion diagram, but without the disk component. So I will also show how our model located on this VBD diagram. So let me explain the one by one. So dashed line shows the models when there is no rotating disk, while the solid line shows there is a disk component in the model. And each line shows has the same inclination of the bicone. So this solid line corresponds to the inclination at 40 degree, and this lower one shows the inclination at the 0 degree, almost based on H mountain. Yeah, that one. And each color shows a different outflow launching velocity. So blue to yellow and red, they gives the larger outflow velocity. And through this line, we gain more extension on the galactic dust planes. So you can see that through this line, the velocity offset becomes more blue shifted because the receding cone gets dimmer. So then also 2016, they don't have the disk component. So you can think that this this dashed line is identical to the BNO 2016 paper. And in that paper, we suggest that the outflow launching velocity from 500 to 1,000 km per second can reproduce most of the VBD diagram region. However, in this work, we also included the rotating disk component. So because rotating this component has the velocity offset almost 0 and very narrow component, so this makes the total O3 velocity and velocity dispersions decreasing. So to compensate for the rotating this component, we need more faster outflow velocity, such as 1,000 to 2,000 kilometers per second. So this is the main change of after our modification of our 3D outflow modeling code. And lastly, I will introduce the AGN feedback in the post-Towers galaxy and with the Gemini GMOS data and NIPS data. So first I want to explain what post-Towers galaxy is. So post-Towers galaxy is the galaxy which experienced the recent rapid quenching within the last 0.1 to 1 giga-year. So as shown in the left figure, so these galaxies are considered as a transition stage between gas-rich merger like ULERCs and the quiescent ellipticals. So this is the transition stage, and since these galaxies experience the recent rapid quenching, so O and B type stars are already dead, but A type stars are still remain. So we can identify these galaxies with the strong H delta observation line, like shown in the right figure. So post-starburst AGNs are the post-starburst galaxies with AGN activity. So they show the post-starburst feature from the H delta and AGN activity from BPT simultaneously. So I introduced the delayed AGN feedback scenario before. So and post-starburst agent PSAs are here. So agents are still luminous, but star formation get quenched. So in the delayed agent feedback scenario, we think that agent feedback may require a certain timescale to quench star formation. So to test this scenario, post-starburst agent might be the best test bed, because we may observe the agent feedback in action, and by studying the galaxies with certain stage in the galaxy evolution history, we can see that when the agent feedback works and when the star formation quenched by the AGN. And also recent studies started to map the post-starburst feature with the IFU data. So in this study, we want to map the H delta observation line with the outflow together and compare and see whether they have spatial correlation or not, so we can get some spatial constraint too. So the goal of this study is to investigate the agent feedback in post-starburst agent and to find the temporal and spatial constraints. So we already selected the post-starburst agents from the OSSY catalog based on H delta and BPT diagnostic, and total 260 post-starburst agents are selected. So we plan to study some demography of the post-starburst agent and compare with the normal agent with the several physical parameters such as agent fraction or outflow kinematics, star formation rate or star formation history, etc. And also among these 260 post-starburst agent, we also selected the 20 post-starburst agent with strong outflows with those 3 velocity widths. So in this GMOS IFU study, our goal is to compare the spatial distribution between the post-starburst feature by H delta and the outflow feature by O3 emission. So in 2021B, 2 post-starburst agents were observed as a pilot study, but there was a B600 grading issue, so H delta was not detected well. And after 23B and 2024A, right now, 2 post-starburst agents were observed with the new grading. So yeah, so this is the current status. And also, we also doing some follow-up observation with the JCMT Scuba 2 to obtain the infrared-based star formation rate of this GMOS sample in 2024A. And the other thing I'm doing now is the one specific target, the NGC 1266. So this NGC1266 is a nearby prototype post-diverse AGN, with heavily studied by the last 15-ish year. So maybe many studies already found that the cold molecular outflows and ionized outflows, neutral outflows in this target. And also they found some interesting shock signature shown in the left bottom figure. So the left figure shows the H alpha radio and X-ray images of this, the central region of this target. And you can see that the spatial correlation between them. So we are previous studies suspect that there is some shock or shock induced by outflow or induced by jet, etc. So what is the origin and the role of the shock in this target is still remain elusive. So, and also this shock can, whether this shock can be an efficient channel of the AGN feedback. So I'm mainly analyzing the archival K-band Gemini NIPS data of this target. So I already obtained the H2, the molecular hydrogen line kinematics, and also so you can see the top on the top panel, you can see the 1 arcsecond extracted spectrum of this target with the Gemini NIPS data. You can see the strong molecular hydrogen line and also the bracket gamma line, etc., and CO absorption band. And bottom right figure shows the H2 flux velocity and velocity dispersion maps. You can see the very complex kinematics at the center of this galaxy. So it may indicate that there is some outflow or inflow or any other turbulence, etc. So we are studying on this. And we also use using the archival VLT Muse data. So the bottom left figure shows the O3 velocity and H alpha velocity maps. So these are consistent with the previous results from Davis 2012, which is based on Gemini GMOS IFU data. And also with the VLT Muse data, we can see that their central region all dominated by the liner photoionization, which is consistent with the shock scenario. So I will study this target more specifically. So this is some of the preliminary result of this target. And yeah, that's all for today's talk. And I'm happy to take comments or questions for my talk. Yeah, thank you.
Questions?
I'll be hearing naive questions, going out of my field, but isn't AGN activity variable with time? It's thought that a lot of AGN vary dramatically in time, and you're looking at some correlation with what the AGN is doing, well, now, so to speak, compared to the star formation activity, which is reflecting what was going on at some time in the past. Is that a complication or not?
You mean the time scale of the agent, the variability time scale, you mean?
The
duty cycle.
Star formation is possibly affected by when the flow reaches it, which is sometime after the activity which you're observing.
Oh yeah,
Reflecting what the AGN was doing at some time before.
Mm-hmm.
Is that a complication? Or?
Yeah, I think that's the main problem in our field. I think is because AGN duty cycle maybe 10. Sometimes it flickers very short time scale, maybe 10 to the 5 years or 10 years. So we need to constrain that part very specifically. But I think there's no clear answer with the observational thing. But in this case, especially post-Star stage, and we are thinking that they experience some gas-rich merger. So if they flicker, anyway, they have some continuous mass accretion on the AGN. So maybe there is a general if impact by the AGN should be shown if there is an responsibility of AGN to the star formation quenching in the galaxy. So yeah.
Any other questions?
I have one. So you see a positive correlation in the first part of your talk between SFR as measured by far infrared proxy and AGN activity, but there is a decent amount of scatter in your sample. So there does seem to be some systems where there's a deviation and the star formation looks low relative to the expectations of the AGN activity. Have you looked specifically at those systems, and might those be systems that are already starting to quench?
I think the main issue is the error in the sample. So they are mixed with type 1 and type 2 AGNs. So they have pros and cons. So type 1 AGN type 1 AGN has relatively accurate black hole mass, but they had no accurate star formation rate or any other things, while the type 2 AGN has a relatively accurate star formation rate or stellar velocity dispersion, while their black hole mass is still not accurate. So maybe this scatter mainly occur mainly due to these observational or these systematic errors, I think. So that's my guess. Yeah.
So do you see the scatter is symmetric about the bit, or do you see biases associated? So if it were just, temporal scatter, or there was a proxy issue for a certain type of AGN class, you would expect the scatter to be symmetric around the best bit relation. Do you see larger deviations to the lower end of that distribution, for example? If you see some sort of asymmetric scatter, that could indicate ongoing quenching.
Yeah, if you devise on this specific specific agent or the galaxy, then we can see some difference between them, I think. Maybe I can am I answering right, or
We can talk later.
yeah, sorry.
Yeah, I guess what I'm driving at is that you see a fairly strong positive correlation, and seems to be significant between star formation activity and AGN activity. In the third part of your talk, you have post-starburst systems, or at least that's how you've selected them, which by definition shouldn't have a lot of star formation activity, but still have powerful AGN activity.
Yeah.
And so there should be an interim period there where quenching starts to occur, but it hasn't fully taken effect yet. And so you should start to see some of these galaxies which are on their way to being quenched rather than just fully quenched versus an incredible amount of star formation activity. So you see the upper right, like basically where do the objects in the upper right of this plot, on the right-hand plot, go? How do they transition to being into the post-starburst phase, or are they completely separate branches of evolution?
I think that point I need to answer with the post-starburst agent study. So I think the post-starburst agents are some kind of transitional stages of it. So maybe I don't know why they stay the agent still turns on, but yeah, I need to that part I need to study more in the part 3 studies. So yeah, yeah.
You see, so you're doing a JCMT follow-up of these post-starbursts. Like if you just do an H delta selection, you can pick up dusty star-forming galaxies. Of course, you pick up the two ends, the two extreme of the distribution. You either pick up post-starburst galaxies that have no star formation activity, or you pick up obscured starbursts. And so going to the IR is very important. Have you seen any evidence of star formation activity among your sample?
Yeah, we first thing we selected this target only based on the H delta signature. So, and I know the recent report about the far infrared access of the post-starburst galaxy. So when I proposed the JCMT data, I already performed the SED fitting of our target. And I think, as I remember, half of them are located near the main sequence, while the other half is located below the main sequence. So I think it would be interesting to distinguish between them, how different they are and why they are different. So I think that's the important part. Yeah.
Any other questions? Any questions online? If not, let's thank our speaker again. So both our grad student visitors will be here the rest of the day and tomorrow, and then they will be going up to the summit Thursday. So if you want to meet with them and you haven't signed up, let me know and I can try and fit you into their schedules over the next day and a half. So, yeah, thanks for coming.
Was someone thinking